here in 16.3, we're going to look more at, now that we can figure out the number of outcomes, can we use that to get an actual probability or a chance that something might happen? Okay, so if we toss a coin, we got that there's two different things that could happen. You could get heads or tails, and so the standard answer is flipping, let's say, tails is 1 out of 2 options. So why is the answer 1/2, and what does it mean? And so we talked about a little bit ago, it doesn't necessarily mean that every time you're going to get exactly a 50-50 split. If you were to flip a coin millions and millions of times, you should get closer and closer and closer to a 50-50 split. But it doesn't mean that you can't get heads 3 times in a row. It's the theoretical probability. So sometimes, or classical probability, sometimes an event consists of just one outcome. So we call that a simple event. And then, so like getting heads or tails instead of a slew of things that could happen. And then an event that can't happen is called an impossible event. So looking at coins again, since we've seen a whole bunch of these, here's one for if you flip a coin, so write out the whole sample space for if you flip a coin 3 times. And I'm going to rewrite the whole sample space up top here, just so we can take a look and see something. So we could get all heads, we could get heads, heads, tails, we could get heads, tails, heads. I'm trying to do that organized thing where I change them from the back end first, so tails, then move 1 up. Then I could get heads. Where do we got heads, tails, heads? Do we change them both? I guess we could get tails, tails, tails. And I could get tails, heads, tails. And I could get tails, heads, heads. And one more. This is why it's good to think about there's 2 choices, so 2 times 2 times 2, so 8 different things that could happen. You know how long your list is going to be before you start it. So I'll fix this one. Okay, so we get all heads, 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 tails. We have tails, heads, heads. Tails, tails, heads. There's the 8th one. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so what they'll ask you about how many times things can happen. It's nice to have the whole list if you can sometimes to look at and compare it to the question they're asking. So 2 or more heads, how many different ways can that happen? And so notice 2 or more, 3 would count for that. So there's 2 or more, there's 2 or more, there's 2 or more. That one's only got 1, that one's got none, that one's only got 1, there's 2 or more. So that would be 1, 2, 3, 4 out of 8 possibilities. And if I reduce that as a fraction, it's 1/2 or 0.5 is the probability. So it's nice to have the list, so whatever they're describing. So when they do the 2 or more or no less than. All right, here's an interesting one. Toss the same number of heads as tails. Well, we're doing 3 coins, so we can't get 1 1/2, right? We could get 2 and 1, we could get 1 and 2, so there's no way that can happen. So the probability of that is 0, or if we're writing down the sample space, it's an empty set, there's nothing in it. And then toss 3 heads or fewer. So here's an interesting one. You're always going to get 3 or fewer. You could get 3, you could get 2, you could get 1, you could get none. So that one looks like the whole sample space. Or if we were trying to do probability, the chance that that would happen is that's all 8 out of 8 outcomes. So it's a probability of 1. So we'll look at in a little bit. Something that is certain to happen has a probability of 1, and something that's impossible has a probability of 0. You can't have anything less than 0 or bigger than 1. This is a 0% chance, and this is a 100% chance. Okay, in this example, they're looking at free throws. So let's say instead of being a person where we already know their probability, we'll say it's somebody where we don't know what their chance of making a free throw is. So if we don't know their chance of making a free throw, we'll call it P. And so then this brings us to some interesting ideas. So the least they could have if they don't make any, or if they make them all, would be the chance that they don't make any is 0, and the chance that they make them all is 100% or 1. So let's say if their probability that they make the shot, so we'll call that one S, and F is for fail, if their probability they make the shot is, let's say, 70%. So the chance that they make it is 0.7. 0.70 if you like it better to think about it like 70% as a decimal. So 0.7. What's the chance that they don't make it? We'll see this 1 minus thing, since that's the only other thing that can happen, right? It's the entire sample space. You either make the shot or you miss it. There's not a third option. Then 1 minus 0.7 gives us what? 0.3? And so think about this intuitively. If there's a 70% chance that you make it, there's a 30% chance that you don't make it. They have a name for this. We'll see it in a second. It's called the complement. But it's just the idea that if you've already accounted for all the things that can happen, there's no third option. You either make it or you don't. If there's a 70% chance you do make it, there's a 30% chance that you miss it automatically then, because I know that the sample space has to add up to 100%. Okay, here's an interesting one. They have 6 players, and they tell us some of them are from different countries, and some are male and female, and then they give us all the probabilities that they're going to win the tournament. So it looks like this guy's the favorite. He has a 25% chance of winning. It's bigger than anyone else's. Then they could go and ask us questions like, let's see, what's the probability that an American will win? So I got to go back to our list to see, first off, who's American in this list. So it looks like E and F are the only American players. And so if this person has a 16% chance of winning and this person has a 15% chance of winning, the chance that one or the other one wins is 16% plus 15%, so 0.31 or 31% chance. Then they ask, what's the probability that a male will win? So we go back and look at the list, and B, C, and D are apparently all men. And so if we add up all their probabilities, the chance that it will be one of them or the other one is all their probabilities added together. All right, so then just like the coin thing, what if we ask about something that's impossible? So they say, what's the probability that an American male will win? Well, if I go back to the list, E and F, the only 2 Americans, were both females. So if there is no American male in the tournament, then the chance that an American male is going to win is 0, because there isn't one, so it's impossible. Okay, then we'll look at when it comes to the coins and dice thing very often. You'll hear them say something called a fair dice or a fair coin, meaning it's not a trick. All the sides are have an equal chance of coming up, right? It's not like weighted. It's not a trick coin, or it's not two heads or something like that. So that's the same idea. This fancier word for an equal probable space. They all have an equal chance of coming up. And so we can use this idea, if we know how many different things can happen, the probability of any one of them is the chance how many times it can happen divided by the whole sample space. So if I say, what's the chance I get a 2 on a dice? Well, 2 is only one side of the dice out of 6 possibilities, so the probability is 1/6. I know that because I know that all the sides are equally probable unless it's a trick or a weighted dice of some sort. So you hear them say a lot of times a fair coin or a fair dice. That's what they mean, is that it's just normal coin or normal dice. They all have the same odds of coming out. And this is the same idea we were talking about earlier. The complement is if you know the probability that something will happen, the probability that it won't is 1 minus that. So if there's a 60% chance that you win something, there's a 40% chance that you lose. If there's only the 2 options, or if you have the rest of the sample space accounted for, it has to add up to 1, so you can do 1 minus to figure out the chance that something won't happen. Okay, something slightly different than probability is when they give you odds. So when they say the odds of something is, say, 2 to 3, what they're saying is that there's 2 is the odds in favor and 3 is the odds against. They don't tell you in terms of the whole sample space like we do with probability. So how can I switch, say, these tennis ones, these probabilities, into odds. So if I look at these, 8% means there's an 8 out of 100 chance that something's going to happen. And then if you can, you always want to reduce them as fractions. So 8 over 100 reduces to 2 over 25. So 2 over 25 is the probability that this person wins the tournament. The odds of them winning are there's a 2 different ways or a 2 chance that they will win to 23 different ways that they won't win. So they don't give it out of the total. And so how did I get that? Well, if there's 2 outcomes out of 25 where they win, that means the other 23, since this is the total number of the sample space, the other 23 account for times that they don't win. So similarly here, if there's 4 outcomes in which they win out of 25 total, their odds of winning are 4 to 21. There's 4 outcomes where they win and 21 where they don't. The probability is using the total sample space. And so this one, if there's 1 outcome, so this is 1, 2, if the total's 5, one of them they win, that means there's 4 where they wouldn't win. So their odds are 1 to 4 for winning the tournament. So the only difference is they don't use the total as the denominator. Probabilities use the total number of outcomes. So this is winning to losing versus winning to the whole number of outcomes. Okay, if we look at a dice thing, so this is kind of interesting if you've heard of lucky number 7 before. Is there something inherently lucky about 7? Not generally, but when it comes to dice, 7 has more ways that you can roll a 7 than any other number. If we're dealing with dice, they only go 2 through 6, so you could get a 1 and a 6, a 2 and a 5, a 3 and a 4, and then those same objects in reverse. So it looks like rolling dice, there's 1, 2, 3, 4, 5, 6 different ways that you could roll a 7. Notice how the next closest ones, there's only 5 different ways to roll. So a 7 is the most probable outcome. There's 6 ways you can roll a 7 out of 36 different options here. And so same thing, like to get, what do they call this, snake eyes? To get a 2, you can only roll a 1 and a 1 is the only way to get it. So that's much less likely than rolling a 7. And this is the idea we were talking about a second ago. The complementary or the complement is if something does happen versus if something doesn't. And then independent events. If I flip a coin, I flip a coin again. The second one doesn't affect the first one. So it's be careful sometimes. It can start to feel like somehow it would. But if you're rolling dice, flipping coins, they don't affect one another. Okay, and if things are independent, this is the same idea we've been using. If you multiply the number of options together or their probabilities, you get the probability that they both happen. Okay, so let's look at an example of this. So imagine somebody gives you a bet. You toss an honest coin, or they'll say fair sometimes, so there's that word coming out, 10 times. If it comes out 5 heads and 5 tails, you win, and your friend buys the pizza, otherwise you lose. So at first, this seems like a decent bet. You go, well, there's a 50% probability of getting heads or tails, so it seems pretty good. You would get 5 heads and 5 tails. All right, but let's see all the different ways that we can do 10 coin flips and see if this is actually a good bet. So from earlier, we had the idea that you have 2 choices. You could get heads or tails, and so 2 times 2 times 2 times 2, 10 different times gave us 1,024 as our number of outcomes. But now we got to think about, well, how many different ways could you get 5 heads and 5 tails? It doesn't have to be 5 heads and then 5 tails. They could be, they could be all mixed in like this. And so using our combinations formula, and we'll look at more of these or look at the homework example ones. If I have 10 slots and I'm choosing 5 heads or 5 tails, there's 252 different ways to do that. And so your chance of winning is 252 out of the whole sample space. So you actually only have a 25% chance of winning. Your friend has a 75% chance of winning because he could get anything besides 5 and 5 and still win.